exactly make sense. It kind of does. So, section 6.3. Anybody watch Despicable Me for inspiration this weekend? We tried. Okay, so then coming back. We talked about the roller coaster and all this jazz. Oh, we have 6.2. We should have graded. Oh well, too late. We're already into it. We'll grade 6.2 tomorrow. Vectors. If you guys noticed, I don't know if you can tell. Can you tell this is in bold?
No.
Okay, yeah, me really either. It's bold. In the book, they're going to use bold letters to stand for vectors. However, can you write in bold?
I guess
Kind of. You can make it like thick and say, oh, okay, it's a bold. Yeah, no. So because the whole bold thing, yeah, it's great if you're typing, and even then, you guys are like, I can't even tell. You should be able to tell a little bit better in homework when they use bold letters to represent vectors. A better way of doing a vector notation is with this little line up above. Some people use a double-sided, I shouldn't say double-sided, a double tail? Not just awkward. Anyway, some people use both little parts of the arrow. I personally like just a single part of the arrow. It's faster and it looks kind of cooler to me, but anyway, that's the way I usually do the arrow. Some people, you can do both. I kind of save that for geometry and for array, but anyway. Vector, you must do the little arrow above the letter for the notation of a vector because I do not want you writing in bold, okay? Okay. With that, if we were talking about this vector right here, so this is his name. V for vector, it could be any lowercase letter. Not usually Greek letters, we kind of save those for angles, but lowercase letters with some sort of, our book will do bold or with an arrow on top. Remember, does this arrow mean go on forever?
No.
What's it mean? This direction is the force, is the movement, this direction, right? But a vector does not just have direction, which the arrow shows, but it also has magnitude. And so with that, let me show you first of all, a vector, its direction will be theta. Its direction will be measured by theta, which could be a standard position like you see there, or it could be like a compass bearing. They could do bearings for direction as well, and you guys know bearings are sometimes weird and they measure from north or from south. But anyway, direction is shown by the theta, the angle at which it's occurring, referenced relative to something. But for our purposes, mostly standard position. But then magnitude is going to be shown by the length. So the actual length of the vector, just kind of trying to establish for you guys once again, even though there is an arrow, it is not infinite. It does have a set length, and that set length denotes the magnitude, which does not have to be, it sometimes is an actual length, like 5 miles. You're like, okay, the magnitude is 5 miles. But sometimes it could be something like negative 9.8 meters per second squared. It could be a measurement of force, or it could be force, I should say acceleration technically. Or it could be joules, or it could be something else. It could be a different measurement, but the magnitude is some sort of finite amount, and how I put it up here, the length can denote the actual length, but can also be the amount of force, the speed of the velocity. It's the how muchness. I know it's really awkward, but it's the how muchness. It's the, I don't want to use the word force because it's not always force. It's the, I could use the word power, but it's not always power. I could use the word speed, but it's not always speed. So I'm just saying it's the how much, it's the quantity that's being included. Notation for magnitude, Andrew just said absolute value bars, right? Well, kind of. Double bars are the notation for magnitude around a name of a vector. Now hold on, wait a minute. This does not look right, right? That doesn't look right. PQ with one arrow on top? I don't get it. I thought it was a little lowercase letter. Lowercase letter is one way. The other way of saying it is from an initial starting point to the ending point. So you could also say, like we do with geometry with line segments, you could call it PQ, but we still have to put that little, the book might do it bold. Once again, I'm going to do the arrow. We could call it with a lowercase letter, or we could use the initial and then the final. Quick heads up, in this notation, it is proper, it is only correct when you use the initial point as the first point and then the final point as the next point. In geometry, remember, I guess not with rays, but if it was like a line segment, it wouldn't really matter, P then Q or Q then P. But in array, you guys can already, hopefully in geometry, you already knew you needed to go from one direction to the other. But also, in vectors, this is denoting, hey, starting here and headed this direction. Starting at P and going towards Q with a set length. So I wanted to make sure you guys know what that notation is also. There's two different ways. Lowercase letter or initial and then final. Which also shows us the direction, to be honest. Notation for magnitude. We already talked about that with the double lines. I guess you can kind of correspond this to absolute value. Do you guys know what absolute value mathematically truly does, or who it truly is? Or just tell me it makes it positive. That's not the actual meaning of absolute value. That's a trick to remembering. What is absolute value actually measuring?
The distance from the number and 0.
Good. So on a number line, 5. How far is 5 from 0 on the number line? 5 units away, right? How far is negative 5 from 0? It's 5 units away. Absolute value literally measures the distance. You can also think about it, it's the magnitude of the number. So it's not necessarily the direction of, hey, 7 is to the right of 0, 7 places, or negative 11 is 11 places to the left. The sign denotes whether it's to the right or to the left for numbers. And yes, the quantities, of course, there are different meanings for positive, negative. But as far as like the actual placement, the sign shows where the number is in relation to the 0. This has a lot of applications to physics. But the magnitude of the number is the how muchness of the number in the sense of, question, let me try to illustrate. Is 1/2 greater or less than negative 10? Is 1/2 greater than or less than negative 10? Greater. Why? On a number line, isn't it to the right? Another way of saying it, if I have half an apple, is that better than having negative 10 apples?
Yep.
Yes. If I have half $1, is that better than owing someone $10? Yes. Okay, so half is bigger than negative 10, right? Is greater than. Problem. If I was to ask you if a car that's going 0.5 miles per hour versus a car that's going negative 10 miles per hour, which one's going faster? What would you say? Negative 10, because negative 10 is actually a velocity, not a speed, because there's a negative on it. And what it means is the car is moving left at 10 miles per hour. So another way of saying it is whose magnitude is greater, 1/2 or negative 10? Negative 10. But 1/2 is a greater number. Yeah, but whose magnitude? Okay, so that's kind of the idea of magnitude. Magnitude is not really taking into consideration direction with vectors. It's just saying how much is there. Let's go ahead and do this really quickly. We're going to come back to this in a little bit. Some of these things build on themselves. You might see it a few times, which isn't totally bad. Hey guys, can't we take any diagonal line and split it into components? Couldn't we name this guy A and that guy B? How would you find the magnitude? You can make the diagonal, which length I'm trying to find for magnitude, C, or hypotenuse. Good, Ryan, you were saying that, right? So what theorem could I use? Yeah. So one way to find magnitude, if it is not given to us, is to actually think about what we're given, break it up into horizontal and vertical components, is what we're going to eventually be calling them, and then use Pythagorean theorem. Here's something super crazy about vectors. Here's something super crazy about vectors. All of these vectors are equal. Why is that weird?
They don't look equal.
They're not all in the same place, right? But they're all equal. Why are they all equal? Because they all have, well, first of all, I copy and pasted them all. Which means they all have the exact same what? Length. And if I copy and pasted them all, what else do they all have? The exact same
Direction.
Wait, no. This one's like pointed this way, that one's pointed that way. They're not all the same direction. They're the same direction, right? And the weird thing, and this is kind of also introductory to physics a little bit, or the idea of vector diagrams. If I was to, did you guys see any X or Y Cartesian planes up here at all? No. Why? Because depending on what you're talking about, the XY plane is where you put it. So if you were to take a little XY plane with each of their initial points at the origin, what's going to be all of their directions? The exact same. This is very similar to north, south, east, west. You could have an object here that is, what's the way of putting this? Two different boats in the water. Compasses are showing them going the exact same direction, although they're in two very different places on the sea. Does that make sense? Kind of the same idea. Since there is no set standard one Cartesian plane, one x, y, we say, oh, they have the exact same length and the exact same direction. It doesn't matter that they're in different places. And here's another way of looking at it. Vectors, which is kind of crazy, vectors we can actually shift to be wherever we need them. And I'll try to illustrate that a little bit further on. Let's go ahead and look at this example real quick. Shouldn't take us super long. The example is just saying, show their equivalent. There are many different ways of doing this. But the two things that we have to show in order to say that they are equivalent is same length and same direction. Does anybody have a way to prove same length? Now pause. We can try. That's a good idea.
Distance formulas.
How could we name the top vector? How could we name it?
RS.
So we could say RS with a little notation. Remember, no bold. That's complicated. We could also say, what's another name for him?
Vector number 1. V.
I'm just going to name it V. We don't usually use numbers for vectors. Good idea, John. The lowercase letter V. Okay, so RS is equal to V. And we could say that we're looking for, double lines. If I'm going to put a number on it, I have to put the notation for magnitude. That's only one piece of the vector. So double lines say I'm talking about length specifically. How could I figure out the length of RS or of angle V? Distance formula. Sure. But Andrew, was it you that said make a little baby triangle? Oh, okay. So let's look at this one. How is he a triangle? Well, guys, what's the horizontal distance for the leg that's, I don't know, we could call it the adjacent to the angle of rotation? What's this horizontal? 3, because it's 4 minus 1. You could say x2 minus x1. Oh, it's the distance formula. That's right. So you can call this guy 3, and then what would his height be? 4 minus 2 is 2. Good. So we would say he's going to be the same thing as the square root of 4 minus 1 squared plus 4 minus 2 squared, which is the same thing as 3 squared is 9, 2 squared is 4, square root of 9 plus 4 is square root of 13, right? How could we, that's not what I'd like to do. How could we find the length of the second triangle? It's supposed to be right here. There. Alright. Who's the second vector, first of all? What can I name him? Yeah, PQ, if we're going to follow the same pattern. We could name him vector PQ, or we could name him vector U. And how would I find his length? Can I do his change in x's and his change in y's? Would that be 3 minus 0 squared plus 2 minus 0 squared? Some of you can already tell just by looking at the picture it's going to be 3 and 2 again. So therefore 9 and 4 is going to be square root of 13. Do they have the same length? And the answer is, of course they do. Same direction. How do we figure that out? One way is slope, seeing if they are sloped the same, because if they are parallel, which means same slope, Then we could say the direction is equal. There's actually another way as well, but let's start with slope. So what's the slope from one point to the other of PQ?
Two over three.
Yes. Positive 2 over 3. Why am I saying positive?
Going to the right.
Because I'm going up and to the right. So I could say positive 2/3. What's going to be the angle? Do you guys see how I'm noting it? You can note it with vector u, you can note it with vector pq. But then vector rs, what would its angle be? What slope, I should say? I apologize, I'm saying beta, and we're not finding beta, are we? We're finding m. Okay, rs, same thing, right? So if we needed to defend our answer, we could say parallel vectors will have the same direction. Since both vectors have the same slope, they are parallel. It's kind of like a little geometric proof. We can set it up if we wanted to. But what's the other way? I just found the slope because that's what Patricia said, but Thomas, what else could we do?
You do log cosine?
We could do law of cosines, but remember law of cosines, law of sines is best for non-right triangles because there's easier stuff for right triangles. So what could we use for our right triangles? Yeah, inverse trig. And for instance, since I see the 2 and 3, which is a lot prettier than the root 13, couldn't we use tangent because we have opposite and adjacent?
Yeah.
So we could say, oh, hey, that slope indicates that they're going to have the exact same angle. Because to find the angle for PQ, you take tangent inverse of 2/3, and how would we find the angle for RS? Tangent inverse of? Oh, of course they're the same. I don't even need to find it. They're the same. And this is also further introducing you guys to the idea about how the slope of something relates to its tangent. Calculus. Anyway. So, we're proving it. Same length? Check. Same direction? Check. All right, let's keep going. Let's define these snazzy things that I've been calling components. Let's define these snazzy things I'm calling components by looking at a vector rs. Why does the r come before the s?
Because it's
It's the proper way, yeah. Now, you guys said something weird last week, if I remember right. I figured it out a little bit too late. I was like, wait, did I really just? Okay. When we're talking about vectors, we could call R, first of all, the initial point, which is what I've been saying. And we could call S the final point, which sometimes relates to where something is initially and where something ends up finally. But sometimes, like with forces, it doesn't quite mean the same thing. But we could call R the initial point, we could call S the final point. But another way of noting that, we could also call the initial point the tail of the vector, and the final point we would call the head of the vector. I think last week I said the arrow was the tail, but that actually doesn't make sense if you think about, a comet. Comets have tails, right? Cats and dogs have tails. Question, where are the tails?
at the end.
At the back. True. And where's the vector going? Where's the force pushing? So where's the back of the vector? Got it. So it makes sense logically. I don't know why I called the arrow the tail last week. Something weird was going on. But the tail is the back point or the initial point. The head of the vector is the front part, what we would call the final point. Now, if we want to show the vectors using its points, let's go ahead and establish what this point could be. So it looks like this might be, let's see, R over 1 up 2 maybe? Does that sound good? So we'll call R the point 1, 2. What do you guys think S might be? 2, 3, 4 maybe? Negative 1? That sound good? So we'll call S for negative 1. Okay, if we wanted to show the vector using its points, using its components, We just use the components to find the magnitude using Pythagorean theorem. But what we could say is we could actually name this vector with its points, and here's how we would name it. We would name it by taking, I'm going to write this off to the side, the final minus the initial. The final minus the initial. And we, excuse me, to take the x value, which is 4, of the final point, minus the x value of the initial, which would be 1, comma. We can take the y value of the final, which would be negative 1, minus the y value of the, oops, not comma, I apologize, minus the y value of the original, which is 2. And that would end up getting us 3, negative 3. This is what we could call one other version of noting or showing a vector, using its points. Now, it's always final minus initial, so we could do, in a sense, x sub f minus x sub I, if you want to think about it that way, final minus initial. This would be y sub f minus y sub I. The y of the final minus the y of the initial is ultimately what we did. But that ends up getting us the component form. And this component form, there's multiple ways of writing it. We could call this component form. And what it shows is to get from the tail to the head of this vector, you'd have to go down 3 and right 4. Now, hold on, wait a minute. It's 3 then positive 3. What if I was to write it a different way? Isn't the first part of an ordered pair always an x? And wasn't this found from a change in x's, so it would be a better way of writing it? Forward 3, down 3. Forward 3, down 3. So to get from the tail to the head of a vector, I go forward 3, down 3. It's kind of showing me the components. And it's just found by subtracting, we'd say finding the displacements of the x's and the displacements of the y's. But final minus initial of the x's, minus initial of the y's. This is another way of noting this vector. And the magnitude is as simple as, once you go ahead and find those horizontal components, is taking the final the final x minus the initial x, change in x's, the final y minus the initial y, and squaring, which we could call, in a sense, if it helps, the square root of a squared plus b squared when you solve for this to be a and b. If that helps. But it's really just Pythagorean theorem, to be honest. And a picture might do more than the formula does. A couple quick notations. 0 vector, guys, these letters are bold, but I put the arrows above because you're not writing in bold. To remind you to be drawing your arrows whenever you write a vector. A 0 vector is going to have a component form of 0, 0, and the reason is because it doesn't go anywhere. It has no length. So it starts at the point and ends at the point. It doesn't go anywhere. It doesn't have any magnitude. And then a unit vector is a vector with a length or a magnitude of 1, but there are many different ways that we could have many different components that would make 1. For instance, why don't I just write 1, 1? Well, if I wrote 1, 1, wouldn't that have a magnitude of 2? That doesn't work. How about 0, 1? Could that be 1? Yeah, because 0 plus 1 would have a square root of 1. 1, 0, that would work. 1 plus 0 could have a square root of 1, but there might be other ways as well. A unit vector has a length of 1, but there are many different ways that we could get 1. Very many different a's and b's that, when squared, could get 1. Okay, so this is called component form once again. Component form, you have this, we get to call them side carets, because a caret is like an arrow for exponents, right? We can call them side carets. And the A represents how far over, to the right or to the left, depending on positive or negative, how far over horizontally from tail to head, and then B represents how far up or down, how far vertically from tail to head. Boop. So, how can we find the component form? Wait, there are no labels. How do we even talk about this guy? What do you guys want to make him? We can name this side, what do you want to do? Okay. And then name this one. Okay, so what vector is this? Because remember, it has to be tail to head, has to be initial to final. And the arrow is where we're ending up. That's okay. Now what? There's only one right way to subtract. Are we doing L's x and y minus K's x and y? Or the other way around, K's x and y minus L's x and y? Huh? Because this is our final, and this is our initial, if that helps. So we have to subtract. So what do you guys got? -3, good. And I'm just going to show the work as to how, and then what's the next one? Good. So we do x minus x, and then y minus y, and we end up with the final component form of -3, +2. And does that also make sense with horizontal, left 3, vertical, up 2? Exactly. It's as easy as the finals x's minus the initials x's, and the finals y's minus the initials y's. Does that make sense? Let's figure out what's going on with vector operations. What if we have more than one vector? Because you guys saw those roller coasters, right? Weren't there more than one vector, more than one force acting at a time? If there's more than one force acting at a time, to find the net force, we have to figure out mathematically, well, how do we put more than one vector together? Well, first of all, before even putting more than one vector together, which will be vector addition, how do we do scalar multiplication? What if they were asking us, no, careful, what are you guys going to have to put above all these little bold V's? Sorry, above all the bold letters. Good, good, good. When the book puts bold, you put arrows. And that includes when you're writing directions and problems. We're talking about vectors. Scalar multiplication. Let's say in some way, shape, or form there's a force, but all of a sudden the force gets doubled or tripled. How do we do that mathematically? Well, if we want to double V, or if we want to multiply just in general, any constant C times V, if we double it, we would just multiply the x's by 2. So with any constant, we can just multiply the x component and the y component by whatever the constant is. Scalar multiplication, be careful saying distribution. That's not technically what we're doing. But it does end up looking like distribution. If we double a vector, in order to double him and have him keep going the same direction, we start with his initial. We call it V1, which is the horizontal component. V2, which is the vertical. If we want to double that guy, we need him to be twice as long. And to make him twice as long, we need V2 and V1 to be twice as long as well. If we double the legs, we'll get double the hypotenuse. Interesting. Let's see. So there's our 2V, and here's our original. What if we want to add two vectors together? Is it really as easy as it might be? What do you guys think? Just naturally. It's as easy as you probably hoped it was, but weren't quite sure if you could say. Add the x components, add the y components. But in a vector diagram, that gets a little rough. So if we were to take a vector v with his own v1 and his own v2, and take a vector u with his own u1 and his own, nope, sorry, ones are the x's, right? The horizontal. u1 and u2. How would the picture look if we tried to add the two together? We would go v1 and we would add together u1, which means this plus the little bit, right? So that would be the u1 plus v1. And then I would do the v2 plus u2, but what's going to happen? If that's going up and this one's going down, they're going to work against each other, right? So it's going to be v2 minus v2 minus, there we go, u2, which would end up having him just go up, well, just a little bit. That's weird. So let me show you pictorially what that looks like. It's what occurs when you move one vector head to tail with the other. So u1, I should say v plus u, ends up getting, hey, it's your first net or resultant vector. This is your resultant or your net, like you guys saw in those roller coaster pictures. Alright, we have some more to do tomorrow, but we got a good start today of naming them and multiplying and adding them. Start homework, see where you get stuck, but look at your test and have questions for Thomas. Bye guys. Thomas.
Sorry, Jonathan, I haven't told anybody what you